All of you switch on the camera first. I said, is my voice not reaching you? Okay, now you have heard it. आज का चेहरा देखने लायक है because yesterday I have given you so many pages to study. हाँ, दुखी दुखी तो लग रहा, सबका चेहरा दुखी दुखी लग रहा. Fine. Instead of so many pages, had I given you so many sweet boxes or chocolate boxes, चेहरा बदल जाता है. Fine. So today I will go into a different chapter, that is forced vibration. But let me slightly revise. We have studied free vibration in absence of sustained force. Remember, even free vibration begins with a force. Impact is a force. Impact is a force, but it doesn't remain sustained. So if the force comes and goes out, we don't call it a forced vibration. So far we have studied free vibration, number one. Number two, we have studied single degree of freedom, not multi-degree of freedom. Number three, we have mainly taken damping to be viscous. So this is our starting point. We started with simplest thing. Damping is viscous, single degree of freedom, and free vibration. Now in another 1 month, we will go up the ladder. Now we'll go up the ladder. Gradually, we will make it more complicated. So the first complication is, let us go to forced vibration. Second complication is, we will go to multi-degree of freedom. Single degree of freedom से हम जाएंगे 2 degree of freedom. Can anybody give me a real life application where a 2 degree of freedom will be more appropriate than single degree of freedom? कुछ नजर के सामने घूमते हैं? All of you know that. Two-wheeler. When I'm saying 2 degree of freedom means what? Two-wheeler. Motorcycle or scooty. Two-wheeler ideally is a 2 degree of freedom. We have a spring front suspension, we have a rear suspension. That is ideally a 2 degree of freedom, but we can even make a single degree of freedom model of it. We can make it. It will not be a correct model, but we can make it. But if you ask me, a 2 degree of a two-wheeler is ideally 2 degree of freedom. Similarly, a car is actually 4 degree of freedom. There will be many more degrees of freedom in car, but even we can represent it as a 2 degree of freedom initially. So degree of freedom may start from single degree, but gradually the degree of freedom, if it increases, our model becomes more and more representative, but at the cost of mathematics. At the cost of mathematics. As we increase the degree of freedom, mathematics become more and more complicated. Okay, so we will first discuss single degree of freedom, free vibration, viscous damping. That is over. Today I will start next higher ladder. So what is the next step in the higher ladder? Forced vibration. फिर फोर्स्ड वाइब्रेशन में नेक्स्ट हायर लैडर क्या होगा? सॉरी, नेक्स्ट हायर लैडर इज फोर्स्ड वाइब्रेशन विथ विस्कस फ्रिक्शन डैम्पिंग. नेक्स्ट लैडर विल बी फोर्स्ड वाइब्रेशन विथ नॉन विस्कस डैम्पिंग. Next higher ladder will be 2 degree of freedom, free vibration. Again 2 degree of freedom, forced vibration. Next higher ladder will be multi-degree of freedom, free vibration, multi-degree of freedom, forced vibration. So this is how you will reach from ground level to फर्स्ट फ्लोर ऑफ द मैकेनिकल डिपार्टमेंट। 1 महीना लगता है, ठीक है। एंड दिस इज 1/3 ऑफ द सिलेबस, बट इट विल टेक एटलीस्ट 1 month, समथिंग लाइक 20 lectures, 18 lectures, something like that. So let me go to our immediate next ladder, forced vibration of single degree of freedom system, having discussed damping. But before I go, any feedback from you how the subject is going? वैष्णवी कैमरा ऑन नहीं है, जीवन चल रहा क्या साइड बाय साइड?
नहीं सर, डिवाइस अलग है।
डिवाइस अलग है मतलब मोबाइल है? ओ मैं
हाँ
समझ
सर।
गया। नहीं नहीं, मैं समझ गया। यू आर साइमल्टेनियसली अटेंडिंग रिन्यूएबल। अरे 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 अरे, यू आर सब्यसाची। यू नो द मीनिंग ऑफ सब्यसाची?
नो सर।
हाँ, यू डोंट नो?
नो सर।
अरे अरे अरे, I mean somebody who is expert in doing things with both the hands.
सर अटेंडेंस चाहिए तो।
बिल्कुल, नो नो, आई एम नॉट कंप्लेनिंग यू, लेकिन वाइब्रेशन के साथ रिन्यूएबल एक साथ अटेंड करोगे तो पता नहीं क्या होगा, मतलब दोनों मिलके तो खिचड़ी हो जाएंगे। चलो, द मैटर इज अप टू यू, आई कांट से एनीथिंग, बट एटलीस्ट समबडी इज, आई मीन दिस इज, मे बी कॉन्वोकेशन में एक स्पेशल डिग्री हम देंगे वैष्णवी को। हाँ, we will state we will mention that somebody who has simultaneously attended 2 subjects, एक special degree देंगे। To share, I talked to Richa yesterday night, but then today let me share it with you. Even Dean was surprised knowing that few students are attending this class in addition to their normal lectures. Dean was surprised कि VNIT में ऐसे स्टूडेंट होते हैं क्या? आई टोल्ड हिम दैट कि ऐसे कुछ पागल स्टूडेंट है। VNIT में एक ही पागल टीचर था, कौन था? सो यू हैव गॉट द हिंट। कौन? बोलो, जल्दी से बोलो। थोराट सर, है ना? उनको एक सब्जेक्ट पढ़ाने देते, 2 सब्जेक्ट पढ़ा देते। उनको हफ्ते में 3 क्लास लेने बोलते, वो 5-5 घंटा लेते हैं। आप हमारा एमटेक स्टूडेंट उनको देखा नहीं, बराबर है। यूजी स्टूडेंट्स, आई थिंक यू हैव सीन हिम, एम आई करेक्ट? थोड़ा सर को देखे हो कि नहीं देखे हो? देखे हो तो हाँ, तो अभी कॉलेज में एक था ऐसा पगला। पगला मीन्स आई एम पुट सेइंग इट इन ए गुड वर्ड, नॉट बैड वर्ड। हम खुद पागल है इसीलिए उनको पागल समझते हैं, वो अलग बात है। तो व्हेन आई टॉक टू द डीन यस्टरडे, डीन बोला अरे ऐसे स्टूडेंट भी होते हैं क्या? बोला ऐसे स्टूडेंट भी होते हैं, बराबर है। चलो, लेट मी आस्क यू अ सिंपल क्वेश्चन। व्हाट इज द नेम ऑफ दैट जेंटलमैन हु वाज प्रेसिडेंट ऑफ बोइंग? किसी ने ढूंढ के निकाला? 24 घंटा दिया था मैं। आई नो व्हाट यू विल से। बोला हमें क्या लेना देना है, हाँ, दूसरे कोई प्रेसिडेंट बना तो हमें क्या फर्क पड़ता है ना? दैट इज योर एटीट्यूड। एनीबॉडी हु कुड नो, हु कुड फाइंड आउट? रिचा?
सर इज इट दिनेश सर?
Kesker. Dinesh Kesker, you are correct. Dinesh Kesker, 1975 pass out. No, you don't mind because I talk lot of additional things. Then I will stop saying. Sabba?
Sir, no problem, sir.
नहीं, नो प्रॉब्लम, लेकिन कुछ लोगों को चेहरा में प्रॉब्लम दिख रहा। अदरवाइज मैं ये सब बातें बिल्कुल नहीं करूंगा। बट एज यू नो कि आई कॉल देम एज चटनी ऑन योर मेनू। कभी कभी मेनू चटनी के कारण बढ़िया बन जाता है, ठीक है। तो हमारा वाइब्रेशन ऐसा ही एक मेनू है जो नोबडी विल लाइक टू हैव इट। बहुत ही तीखट मेनू है ये। दिस इज भिवापुरी मिर्ची का बना हुआ मेनू है, तो उसके साथ चटनी देना पड़ता है, देन ओनली इट बिकम्स इंटरेस्टिंग। तो दिनेश केस का 1975 बैच, 1975 बैच ऑफ VRCE इज वेरी फेमस बिकॉज हेमंत करकरे। अब बोलोगे वो कौन थे? Now you will say, who was that gentleman? Hemant Karkare, do you know? Who was the ATS police chief in that Taj Hotel terrorist event. He died that day fighting with them. He was 1975 graduate of the same batch, PRC. So Dinesh Keskar is also 1975. He has retired now. लेकिन दिनेश केसकर started his schooling from अमरावती और उनके स्कूल के उसी क्लास में उनके क्लासमेट थे बोब सेट्टी सर. You have not seen him because Bob Setti sir has retired in 2019 and you took admission in 2019. You haven't seen. So going के and who is the other chap? Airbus किसी ने ढूंढ के निकाला?
There's
Richa?
some Ajinkya, I am not sure of the
आशीष सराफ
अजिंक्य सराफ. अजिंक्य सराफ. साहिल कहाँ से तुमने कांटेक्ट भी कर लिया उनसे लग रहा?
No sir, after you told I went on LinkedIn.
You went to LinkedIn, but don't you think कि हमारे VNIT स्टूडेंट्स को एक खबर भी जानना जरूरी है? You should be proud that otherwise what you will think भाई हम तो IIT सोचे थे, कहाँ से VNIT मिल गया, हम सब बेकार है. ये देखो ये लड़का कौन है? ये कुछ और, ये नितेश और कुछ ये कर रहा और कोई असाइनमेंट बना रहा साइड बाय साइड. हाँ नितेश?
No, sir.
हाँ, you are writing. Are you
I
writing a love letter now?
No, sir.
तो
I
क्या
am,
लिख रहा?
sir, writing
तुम भी
names.
वैष्णवी जैसा है ना, इधर मोबाइल या लैपटॉप ऑन कर दे, उधर अपना काम कर रहा.
No, sir.
ऐसे लग रहा मुझे. Anyway, so let me tell you one thing that I always say that VNIT students are as good as IIT students. लेकिन पढ़ने का ढंग बदलना पड़ेगा. Okay, if you don't exert yourself, you cannot compete in the current world. Current world has become highly competitive. Let me tell you, we always, every year we produce 10-15 good students जो इंडस्ट्री में जाने के बाद, I will give you the feedback of one of the topper of 2016 batch. He is in US now. He joined Reliance Energy. When he joined the company, he told me कि सर आई एम नर्वस. हम बोला क्यों इतना नर्वस क्यों है? बोला सर हमारे साथ बाकी सारे इंजीनियर्स IIT से आए हुए हैं, हम 2-3 लोग सिर्फ NIT वाले हैं. After 3-4 months, he gave me the feedback कि सर हम उनसे कोई कम नहीं है, हमें भी उतना ही मालूम है जितना उनको मालूम है. That is the feedback he gave me. So never think that just because you have joined VNIT, you are at a disadvantage. ऐसा नहीं है, लेकिन पढ़ाई करना पड़ेगा, वो बात तो सही है. Fine. And why I am saying, you know why you should give value to this advice from me? यही चीज और कोई बोलेगा तो उसको शायद तुम लोग वैल्यू नहीं दे सकता है, लेकिन मेरे बात को वैल्यू इसलिए देना होगा क्यों? बिकॉज आई एम माई सेल्फ अ बीटेक फ्रॉम IIT and almost 100 teachers in IIT, they are my friend in all IITs. They know me and I know. So I know what's happening in IIT. आज का IIT वो IIT नहीं रहा जो पहले था. Anyway, so with this background, I think I have given you enough appetizer. So let us go for the menu. ठीक है? Having this much of appetizer, अभी कोई भागेगा नहीं. अभी सब vibration सुनेगा. ठीक है? So this much appetizer was needed because we are going to enter in a difficult mathematics of complex number. Let us see how mathematics can solve vibration problem. So, अरे हाँ बराबर है. Is it visible?
Yes, sir.
Okay, so today we will start a difficult chapter, forced vibration, but forced vibration of single degree of freedom with viscous damping. ठीक है? तो चलो.
Yes, sir.
This is the example. I mean, this is the picture. This is the picture. Now, a forced vibration picture need not be drawn like this. It could have been drawn with a single spring and single damping. हमने ऐसा क्यों किया? I mean, there is nothing wrong if I saw only one spring below it and only one damper below it. Nothing wrong, absolutely nothing wrong. लेकिन ऐसा हमने क्यों किया? If I draw a single spring, single damping, what will be value of the spring? Stiffness? Single spring. See, I can replace this by a single spring. What will be value of that single spring stiffness?
K.
It will be K.
Okay.
And if I replace by single damper, it will be C.
C.
So why I am doing a drama? ऐसा हम दो अलग अलग क्यों बनाए? दो पैर क्यों बनाए?
Sir, for balancing of the mass.
No, not balancing. Basically, I am discussing a machine placed on the floor on an isolator. So what is isolator? We will discuss after 1 week. Isolator is something, is a device that possesses spring stiffness and damping simultaneously. Spring stiffness and damping simultaneously. So a rubber pad, we can call it an isolator because rubber can compress and provide stiffness. Rubber can also damp out energy. So even a helical spring, we can call it isolator. But helical spring damping is very, very small. The problem of damping helical spring is stiffness is very, very high, but damping is very, very small. But anything that possesses both stiffness and damping, we call it an isolator. So I have a machine. Now, why I should go for this isolator in between? A machine, we can fix up the machine directly on the ground with the 4 bolts. We don't do it in industry. Whenever we have to fix up a machine on the floor, we put an isolator between the machine and the floor. Why? Answer will come after 1 week. But this is basically a real life representation where we have isolator. So a machine is put on 4 bolts. A isolator इधर के दोनों बोल्ट की रिप्रेजेंटेशन है और ए आइसोलेटर फ्रंट की है, ए आइसोलेटर रियर की है. So now for mathematics, although this is to represent an actual scenario, for mathematics we'll replace it by a single spring, its value is K, a single damper, its value is C. Then what is the equation? The equation is mx double dot plus cx dot plus kx is equal to ft is equal to ft. बराबर है. Now the thing is that अरे मैं यहाँ पे क्यों आ गया? Unbalance में I have entered unbalance. Okay. So I have opened up a wrong PPT, forced vibration, but ठीक है, चलो. mx double dot plus cx dot plus kx is equal to ft, and let us assume that the forcing function is f0 sin omega t. ठीक है, let us assume that the force is a sinusoidal force, f0 into sin omega t. So we are discussing forced vibration when the force is a harmonic force. ठीक है? Now, I cannot use the remaining part of the PPT here. ये थोड़ा अलग discussion का है. So you have to write everything on your notebook now. You say that right hand side ft is f0 into e to the power I omega t. You replace ft. You write down. Now you have to write down yourself. I cannot use my PPT anymore. So I am speaking out, you write down. We assume a complex force ft is equal to f0 e to the power I omega t. You expand f0 e to the power I omega t, क्या मिलेगा? You expand e to the power I omega t, क्या मिलेगा? इसी 5 में this is something else. 4 4 4 4. अभी अपने आप एक्सपेंड करो, क्या मिलेगा? Let me see if I have that particular PPT with me or not. Otherwise, today everything will be on black. That's why I prefer blackboard. Vibration 4. ये अलग है. Okay, I'll go back to same PPT. No problem. I'll go back to same PPT. But I'll ft is equal to क्या लिखा है? f0 e to the power I omega t. Now f0 e to the power I omega t, it becomes f0 cos omega t plus I f0 sin omega t. ठीक है? So now you solve the equation. Now you solve a different equation. Now you solve a different equation. mx double dot plus cx dot plus kx is equal to capital F0 into e to the power I omega t. Solve करो. Solve this differential equation. कैसे करोगे? You know how to solve differential equation. You assume x is equal to, I think I have to drop it क्योंकि मुझे बिना पीपीटी का तुम लोग समझोगे नहीं. प्रॉब्लम वही है. Let me dig out. Today I have opened up a different PPT and I am missing that PPT. Unless and until I bring that PPT, you will not be able to understand. Because y is not there. Okay, I'll use this PPT but in a different manner. चलो,
Sir,
हाँ बोलो.
sorry for the interruption, but yesterday at the end of the class, you said you'll be starting the Lagrange form.
No, Lagrangian is mainly used for multi-degree of freedom. उसीलिए मैं उसको अभी skip करके forced vibration में चले आया because forced vibration for single degree of freedom. Okay, I'll continue with this. Okay, I'll continue with this PPT. Although this PPT is for slightly different discussion, but I will not get out of this PPT. I'll continue. Don't worry. Yes, what I am saying is, in this machine, let there be unbalance. Chalo. So let me slightly modify my discussion. In this machine, let there be unbalance. So if the machine has unbalance, then the rotating force will have one vertical component and one horizontal component. So this is the equation for vertical direction and this is the equation for horizontal direction. Of course, I have made a mistake here. Not mistake, I have assumed that the stiffness in the horizontal direction is same as stiffness in the vertical direction. We can assume it, no problem. It doesn't matter even if they are different. Now what I'm doing here is I'm combining these two. Now I'm creating Z as x plus iy so that capital Z is e to the power I omega t. And my force is a complex force. So what I say, if I can solve for capital Z, then I can obtain x because x is what? X is the imaginary part of the complex force. If you look, you focus on these three equations. Equation number 1, equation number 2, equation number 3. Equation number 3 comes from equation number 1 and equation number 2. But the variable we are using in equation, every one is complex. Z is a complex displacement because it is x plus iy. Excitation is a complex force because e to the power I omega t. So thing is that your question will be, we were far better having equation number 2 and equation number 1 because everybody were real variable. Why we created this equation where force is a complex variable and displacement is also a complex variable? The answer is, we do it to make our mathematics simpler. So how do we make our mathematics simpler? We will see. But before we proceed with the mathematics, let me tell you, this is an imaginary problem which comes from combination of these two real life problem. Okay. Now, x is what? X is the यहाँ पे मैंने थोड़ा गड़बड़ किया है, इसको x पकड़ना चाहिए था, cos omega t है. I have made so many mistakes. Okay, so we will try to find out Z first, and from Z we will try to come back to x. So let us see how we can find out Z. तो तुम लोग एक काम करो, I will say you completely write everything without my help. You have taken ft as f0 e to the power I omega t. लिखे हो ना? Okay. Now you write down that suppose the corresponding solution is Z. Corresponding solution is Z. Then mz double dot plus cz dot plus kz is equal to f0 e to the power I omega t. So we are trying to solve a different differential equation. We are trying to solve a differential equation mz double dot plus cz dot plus kz is equal to f0 e to the power I omega t. Have you written this? Now I will be able to explain you better. First you write down. Let us solve the equation mz double dot plus cz dot plus kz is equal to f0 e to the power I omega t. Have you written this, all of you?
Yes, sir.
Now your question will be that my actual differential equation was this. This was my differential equation. So why I am running away? Why I am running away from this equation and I am trying to solve a different kind of equation? So we will see what is the purpose. But first, let us create another equation and try to solve it. So our new equation is mz double dot plus cz dot plus kz is equal to f0 into e to the power I omega t. Let us try to solve it. But before we try to solve it, let us be very, very clear. Z is a complex variable and force is also a complex variable. So because Z is a complex variable, small z you write down. Now you write down. Let us assume that solution exists. Let us assume solution exists as solution exists as small z is equal to कैपिटल जेड इंटू ई टू द पावर आई ओमेगा टी. इतना लिखो, सिर्फ इतना ही लिखो. स्मॉल जेड इज इक्वल टू कैपिटल जेड इंटू ई टू द पावर आई ओमेगा टी. इतना ही लिखो सिर्फ. स्मॉल जेड इज इक्वल टू कैपिटल जेड इंटू ई टू द पावर आई ओमेगा टी. Let us assume that the solution exists as small z is equal to capital Z into e to the power I omega t. Then it will satisfy the differential equation of the complex. It will satisfy the complex differential equation. If capital Z e to the power I omega t happens to be a solution, then it will satisfy that complex differential equation. तो लेफ्ट हैंड साइड में z की जगह ये वाला डालो. So you put z is small z is equal to, फिर you evaluate this. You evaluate this with this solution. क्या मिलता है अपने को? We get this. आज का थोड़ा सा प्रॉब्लम हो रहा because I am not able to give you a readily available PPT, but you yourself can also derive it without my help. So if we assume that the solution exists, capital Z e to the power I omega t, then this should satisfy this complex differential equation. तो small z is equal to a वाला यहाँ पे डालोगे तो a मिलेगा. मिला कि नहीं? Equation number 4 मिलेगा. And then we say capital Z is equal to f0 by k minus m omega square IC omega. So we have got the value of capital Z. Now this is a complex number. Any complex number can be written as its magnitude and its angle. That is, we call it phasor form or polar form that you have seen in first year electrical engineering. That this z can be written as modulus of z into e to the power minus I5. Why minus here? Because this is in the denominator. So this can be written as modulus z into e to the power minus I5. So this is a complex number. Every complex number can be written as its magnitude into e to the power I theta. Here e to the power I theta is coming out to be negative because the complex number was in the denominator. So this is the magnitude of the complex number. A plus IB is the complex number. So what is the magnitude? Square root a square plus b square. And what will be phi? Phi is tan inverse b by a. It is negative because the complex number was in the denominator. A line थोड़ा समझने का कोशिश करो. Z, we got Z is equal to f0 by this. Now I am writing in a very peculiar fashion. This is from complex definition of complex number. Every complex number can be written as its magnitude and e to the power I theta. Theta is the argument. So if a complex number is a plus ib, its magnitude is square root a square plus b square, and its argument angle is tan inverse b by a. It is negative because the complex number was in the denominator. So tan phi is equal to c omega divided by k minus m omega square. ये भी लिखो. The tan phi is equal to tan inverse c omega divided by k minus m omega square. So we have got z is equal to this value. तो हमारा solution क्या बनता है अभी? Small z is capital Z into e to the power I omega t. And capital Z is this much. तो small z क्या बनेगा? Let us see. Small z is this into e to the power I omega t minus 5. You write all the intermediate steps. So small z now comes out to be capital Z into e to the power I omega t, और capital Z अभी अभी हमें मिला this into e to the power minus I phi. So this comes out to be f0 square root k minus m omega square c omega square e to the power I omega t minus phi. इतना लिखे हो then I will proceed. एक बार फिर से पढ़ो, समझने का कोशिश करो. This is a mathematics we are doing with complex number as the variable. इतना हो गया. किसी को कुछ पूछना है तो अभी पूछो. You can ask me right now. We have done 4-5 lines of derivation. A genuine question should come in your mind that our differential equation was this. This was our differential equation. Instead of trying to solve this differential equation, we are trying to solve this differential equation. Agree? We created this differential equation. We created. We should have solved this differential equation, लेकिन हमने इसके पीछे पड़ गया. इसके पीछे पड़ गया और इसका solution हमें मिल गया. What is the solution? Z is equal to this value. Now, what we can say that this will be the response when force was how much? Force was f0 e to the power I omega t. That is f0 cos omega t plus I into f0 sin omega t. So in our differential equation, whatever was the excitation, that was imaginary part of right hand side. Now let me compare this equation with this equation. This excitation was imaginary part of this right hand side. Then this response will be imaginary part of Z. So this is a theory comes from complex, that in complex theory number, imaginary part always remain imaginary, real part always remain real. So if we have two different complex numbers which are equal, then imaginary part should be equal and real part should be equal. So what I am saying that if I compare this equation with this equation, where f0 sin omega t is the imaginary part of right hand side, then the corresponding response x will be imaginary part of left hand side. So what is imaginary part of Z? If Z is written by this, what will be imaginary part of Z? It will be, you expand it, sine omega t minus phi. So finally, this is our solution. Okay, the mathematics we have done is using theory of complex number. Many textbooks do not follow this mathematics. I prefer it because this is very, very shortcut. We arrive at the answer in 4-5 lines. थोड़ा सा मुश्किल जाएगा. So even if you have not understood it now, you keep on reading it for another 1 hour, you will understand. But finally, you note down this. This is our solution. That the vibration response in vertical direction x will be equal to this. इसको लिखो. We have arrived at the answer using a difficult mathematical route, but this result is important to us today. Fine. How we have arrived is not all that important. That is a part of mathematics, but this result is very, very important. So if we look at the result, हमें क्या, what comment we can make? If we look at the result, what comment we can make? See, xt is what? Xt is how the machine will go up and down. Agree? Xt is how the machine will vibrate in the vertical direction. And we have got a mathematical description of that vertical motion. Now we can show that, see, this is how xt will move vertically. So we have got that mathematical description. But as an engineer, we cannot stop here. We cannot stop here. As an engineer, our job begins from here. We have got a mathematical answer, लेकिन हमें आगे बढ़ना है. So what will be our first statement? All of you, at least यहाँ से 5 statement निकलेगा. सोचो जरा, 2 मिनट टाइम दे रहा. अपने मन में क्या क्या आ रहा, ये आंसर देख के what statement you can make लिख के रखो अपना नोटबुक में. I'm giving you 1 minute. Let me see if you can get all the statements or not. नंदना, नंदना, क्या नाम है इसका?
Nandana only, sir.
नंदना, तुम्हारा नाम नंदना है ना? हाँ, नंदना, करेक्ट नेम. हाँ, lunch will be little late. Okay, will it do?
Yes, sir.
Okay. So all of you, I'll go up to 10 minutes past 1 o'clock. ठीक है? चलो. So let us begin. We have got a result how the machine will vibrate vertically. This mathematics is not that important. For an engineer, the important thing is how he uses this result. So tell me, as an engineer, how will you look at this result? This result, you have done it. You have done a very good mathematical work and you have arrived at this result. How do you look at this result? You can make some beautiful comments looking at the result. What are the beautiful comments? Follow. Common sense.
So vibration does not die with time.
Agree? vibration will never die with time because it is a forced vibration. Okay, so vibration remains. Vibration remains. Now, although this is not the answer I was expecting, but this answer is important for an engineer. Vibration will never die. How, as for an engineer, it is an important sentence? It is very important sentence. Otherwise, that this will lead to fatigue failure. If a vibration remains, I don't know, third year MD2 चालू हो गया क्या? Machine design 2? अरे कोई जवाब नहीं दे रहा.
Yes, sir. Start.
हाँ, तो machine design 2 you will be taught, I don't know, आजकल कौन पढ़ा रहे हैं, you will be taught design of anti-friction bearing. Now, anti-friction bearings are designed against fatigue loading. And generally, the life of anti-friction bearings are taken to be 10 to the power 7 cycles. Okay? So, vibration generally leads to fatigue failure. So, this sentence that vibration will never die, it means if the vibration never dies out, there is a possibility it will lead to fatigue failure. Possibility is definite if the stress is above endurance limit for steel. If the stress is below endurance limit of steel, fatigue failure will never occur. But if it is aluminium, definitely the failure will take place. So that is how this sentence is important. But in today's discussion, I am expecting more important sentences.
There is a phase lag because of
अरे
time.
किसने बोला?
Richa.
अरे okay, I agree with Richa, but this is my second point. This is my second point. First point is vibration is also a harmonic function. Because the excitation was harmonic, if the excitation is harmonic, vibration is also a harmonic function with the same frequency, omega. But vibration magnitude will be different and will have a phase lag. No, vibration will be having a phase lag compared to excitation force. So vibration is also a sine curve. Only thing, the magnitude of this sine curve will be different compared to excitation, and phase of the sine curve will be different. There will be a phase lag. That is number one. Number two, magnitude of this, look at the magnitude of the vibration. Now, as an engineer, I have no control on F0. F0 कहाँ से आ रहा? Because of machine problem. And I said, it is coming from unbalance. Now, I don't know how to do the balancing. I don't know how to do the balancing. Okay? So I cannot reduce F0. I have no control on F0. But as an engineer, can I reduce magnitude? This is the magnitude of vibration. Can I reduce it? So, as an engineer, what do I do?
So increase stiffness and damping.
Bolo, Vinith.
We can increase stiffness and damping.
No, as an engineer, what I will do? Okay. I have got this result. अभी सबसे पहले हम क्या करेंगे? देखो, let me tell you, I am asking an ordinary question, but exactly this is how you will, when you join a company, आपको दिमाग लगाना पड़ेगा. ये रिजल्ट मिलने के बाद हम क्या करेंगे? कोई बता पाएगा? We can do something कि मुझे तुरंत प्रमोशन मिलेगा. बोलो.
We can
हमारा
get
बॉस
the
को भी
term
देखो,
natural
हमारा
frequency.
लेट मी टेल यू, हमारा बॉस जो कॉलेज में पढ़ा था उनकी पढ़ाई यहीं पे खत्म हो गया. सो ही डजंट नो एनीथिंग बियॉन्ड दिस लाइन. तो इसके आगे आप क्या करोगे कि आपका बॉस इंप्रेस होगा? बताओ.
With a few changes, we can convert gain a natural frequency term.
Okay, I'll tell you. I will draw the graph. I'll draw this graph. What is this graph? This graph is now if amplitude. See, as an engineer, I must be worried about the amplitude. As an engineer, my objective will be how I can make the amplitude low, small. Agree? But this amplitude, can I control F0? No. Can I control mass M? No. But I can control K, I can control C, and possibly I can control the rotating speed of omega. No, omega I don't have, sorry, control on omega I don't have. It depends on speed of the motor, but I can have some different kind of control. So what do? I study how this vibration amplitude varies for different omega by omega n ratio and different damping. So this is the graph, how it varies. So if you draw the graph for different omega by omega n ratio and different damping factor, you get this kind of graph. So I'm not asking you to draw the graph, I'm giving you the graph. This is the graph how vibration amplitude will depend on damping factor and will depend on frequency ratio omega by omega n. This axis is omega by omega n. ठीक है? And this axis is vibration amplitude. And each graph has its own damping factor. This graph I am giving you. Actually, you can also generate. After you learn MATLAB programming, you will generate the graph. But this graph I am giving you. Looking at the graph, we can make some important statements. That is, let me go back to the equation. What will happen if damping is 0 and omega square is equal to k by m? What will happen? If c is equal to 0 and
Go to
omega is equal to omega square is equal to k by m, that is omega is equal to natural frequency, what will happen? Vibration amplitude will become
infinite.
infinitely large. This is called pure resonance. If damping is absent, vibration amplitude becomes infinitely large at omega is equal to omega n. Agree? That you agree? Let me repeat again. If
Yes, sir.
damping is absent, that means C is equal to 0, then vibration amplitude becomes infinitely large at omega is equal to omega n. Do you agree or disagree? Mathematically, are you getting it from this result or not?
Yes, sir.
So, as an engineer, what is the first thing we learned? That if damping is absent, never allow omega equal to omega n. And I can further say, never allow omega coming close to omega n. Not only omega is equal to omega n is dangerous, even omega very close to omega n is also dangerous. So please remember, in forced vibration, damping is a villain or damping is a friend? अरे कोई जवाब नहीं दे रहा.
Thanks, sir.
Damping is a friend. We need damping in forced vibration. Okay. We need damping. If damping is absent, the resonance, if it occurs, that means I have to be more careful about resonance if damping is absent. But what is the disadvantage of damping? That if damping is there will be wastage of energy. Some part of the input energy will be lost through damping. Some wastage of energy will be there. But damping will be able to control the vibration amplitude. So from my side, the most important sentence is, if damping is 0, never allow omega become equal to omega n or come close to omega n. Sentence number 1. Sentence number 2. Now, omega should not be very close to omega n, even in presence of damping. Agree? Only thing, it will not be that much dangerous. But even in presence of damping, omega should not be close to. So, second sentence likho. In presence of damping, vibration amplitude does not become infinity. In presence of damping, vibration amplitude does not become infinitely large, but it reaches a maximum value. It reaches a maximum value at omega by omega n is equal to square root of 1 minus 2 zeta square. Square root of 1 minus 2 zeta square. Means, first of all, if damping is there, the maximum value will be large but not infinitely large. And maximum value will not occur at omega is equal to omega n. It will occur slightly before. Omega is equal to omega n into square root of 1 minus 2 zeta square. And this maximum value is approximately equal to f0 by k into 1 by 2 zeta. This maximum value is approximately equal to f0 by k into 1 by 2 zeta. Okay. So, so these are the two most important sentences from my side, but there are many more sentences. और कुछ नजर आता है एक ग्राफ का चेहरा देख के? Can you suggest few more sentences looking at this graph? See, in absence of damping or in presence of damping, we have to avoid this area. The area where omega is close to omega n, we have to avoid. या तो हमें इधर रहना पड़ेगा या तो हमें इधर रहना पड़ेगा. Which side we should prefer? This left hand side or this right hand side? We should prefer this side. Why? Because the vibration amplitude is very, very small compared to this side. So, omega far greater than omega n is more preferable than omega less than omega n. That is another sentence. And I will close with Fourth sentence. The peak occurs. We see that there is a peak value, means the vibration displacement increases, it reaches a peak, then comes down. This phenomena occurs up to damping is equal to 1 by root 2, that is 0.707. If damping is greater than 0.707, then vibration displacement will not show this increasing and then decreasing trend. It will directly come down. Generally, we do not talk about that much of damping. Why? Natural damping never goes that much of high. Even in suspension system also, we don't push that much of damping. So mathematically, we generally don't discuss when damping factor is larger than 0.707 in forced vibration. So we assume that our system has a damping which is much less. So our graph will be something looking like this. So we are interested on the maximum value of vibration, at what frequency it will occur, and if this maximum value of vibration is not acceptable to me, as an engineer, what I will do? If possible, I will change omega. If I cannot change omega, I will change omega n. Can I change omega n? Can I change omega n?
Yes, sir.
Yes, sir. By
Yes, sir.
By changing,
stiffness.
by changing the
By changing-
isolator stiffness.
Yes,
Mass
sir.
of the machine I cannot change. ओमेगा एन इज स्क्वायर रूट के बाई ए. मास ऑफ द मशीन आई कैनॉट चेंज. मशीन को हम काट के आधा नहीं कर सकते. बट आइसोलेटर के I can now go for another isolator. So I can change K. So omega n I can change. As an engineer, I change my omega n. So suppose I double omega n. So you imagine you are having this graph and the maximum vibration was coming out to be 5, which was very, very high. So what do? You replace the isolator and you increase omega n by 2. You go for 2 times more. So omega by omega n abhi 0.5 ho jayega. If omega n increases 2 times, omega by omega n will become half. It will from here, it will come here. तो अभी हमारा वाइब्रेशन वैल्यू कितना होगा? 1.3. So you have reduced the vibration from 5 to 1.3. It is a tremendous improvement. A improvement कैसे हुआ? Simply changing the isolator pad. That's all. हमने नया isolator pad लगाया. Machine का vibration reduced from 5 to 1.3. Now you can go to your boss and ask for promotion and you will get the promotion. So whatever we are discussing, it has practical usefulness. Okay? We will come back to this graph again tomorrow, next class, that is tomorrow. But आज का class ठीक ढंग से नहीं हुआ, so I will advise कि a mathematics, I will send you the PPT. A mathematics जो भी आज हुआ वो mathematics को समझने का कोशिश करो and try to. Tomorrow we will discuss on this graph again and solve few problems. ठीक है? So आज का क्लास इतना ही. किसी को कुछ पूछना है तो बोलो. This graph is very important. Actually, I haven't mentioned. This is why it is 1. Because vibration magnitude amplitude has been divided by static deflection. So this is not vibration amplitude. This is ratio of vibration amplitude and static deflection F0 by K. So this y-axis is known as dynamic amplification factor, DAF. Dynamic amplification factor. Y-axis is actually a parameter called dynamic amplification factor. Tomorrow I will prepare another PPT and discuss those things. चलो आज का क्लास, if you don't have anything, I'm closing the class. किसी को कुछ पूछना है?
Yes, sir. One thing
Apo-
comes to my mind.
हाँ बोलो.
Output upon energy lost will be greater in right side as compared to left side.
Output
Upon energy lost.
energy loss. This graph is not showing talking anything about energy loss. No. This graph is not showing anything about energy loss. This graph is talking about vibration amplitude. So यहाँ से energy loss हम predict नहीं कर सकते. If we want energy loss, we have to derive another formula and we have to find out the answer from that formula. वो हम करेंगे एक हफ्ता बाद. Energy loss per cycle, that is pi C equivalent x square into omega. Oh, but that एक हफ्ता बाद. Right now इस ग्राफ से, from this graph we cannot comment on energy loss. No, we can only comment on एम्पलीट्यूड ऑफ वाइब्रेशन. एनर्जी लॉस के लिए एक दूसरा मैथमेटिक्स आता है, नेक्स्ट वीक करेंगे हम.
Okay.
चलो ठीक है, तो आज यहीं पे खत्म करते हैं. यू कैन लीव, ऑल ऑफ यू कैन लीव.